In this video, we'll be examining our view of the universe. This is chapter 12.1 in your textbook. So the main aims in this video are to examine the history of ideas about the universe and to observe how ideas have changed over time. So astronomy is the oldest science, and cosmology, which is a part of astronomy, refers to the origin and evolution of the universe. We look at the motion of moon, sun, planets and stars and how it impacts on the daily lives of humans in reference to things such as seasons and navigation. So first of all, let's examine the sun. We know, of course, that it's a star, and it's about 80% hydrogen and 20% helium. It produces energy by nuclear fusion of hydrogen nuclei in its core, and we will examine this process later in the unit. Our sun is an average middle-aged yellow star, like 100 billion other stars in our galaxy, the Milky Way. So what's a galaxy? Here's a picture showing several galaxies. It's a large collection of stars, approximately 100 billion, and there are approximately 100 billion galaxies in space. You can do the maths to work out how many stars that is. Here's a neighbouring galaxy of ours, Andromeda. So here we have a diagram showing our sun with the orbiting planets and how it's positioned in the Milky Way, about here. And of course, the Milky Way galaxy is but one galaxy of 100 billion thought to exist. So let's have a look at how models of the universe have developed over time. The earliest models, proposed by Aristotle, had the Earth at the centre of the universe and was known as a geocentric model. It was based simply on observations, and it was ultimately incorrect. Aristotle was a Greek philosopher who lived around 384 to 322 BC. He said that the Earth is round and not flat, and he was correct in that observation. He suggested the geocentric model with the sun and planets revolving around the Earth, and the Earth was surrounded by 55 concentric circles. There were spheres that contained the moon, planets, sun and stars. Spheres had different speeds, sizes and directions, and the detailed model, so further models and predictions could be made from his theory. Models of the universe continued to be developed. The heliocentric model came next. This was proposed by Aristarchus. This has the sun at the centre of the universe and requires the Earth to rotate it, and it's much closer to reality and being correct than the geocentric as we now know. So Aristarchus lived around 240 BC. He suggested the heliocentric model, and the sun was bigger than the Earth. Obviously the sun at the centre of the universe and the Earth orbits it. The Earth rotates on an axis once per day, but the model didn't gain acceptance as it wasn't sufficiently detailed to allow predictions of movement of the heavens like Aristotle's model. So ultimately it was rejected at that time. Now Ptolemy, the Greek astronomer who lived around 140 AD, he decided to go back to the geocentric model. He developed and refined the model proposed by Aristotle, with the Earth at the centre of the heavens and the stars turning in a sphere every 24 hours, with the Earth remaining stationary. He manufactured an elaborate model of circles which predicted observed motion of the heavens. The Roman Church adopted it as the correct picture, and this lasted for over 1,400 years. So ideas and development remained motionless, a bit like the Earth at the centre of the universe. And here we can see an early representation of these spheres. Nicholas Copernicus, working in between 1473 and 1542, then further developed the heliocentric model. He has the sun stationary and at the centre of the universe. Everything else revolved around the sun, and he had the Earth spinning on its axis every 24 hours and travelling around the sun in 1 year. He was a highly accomplished gentleman, as you can see. Obviously, he didn't want the church to find out, and he published his ideas just before his death. Parallax, and we'll explain what parallax is shortly, was not observable due to the immensity of the universe. His work was branded heretical and against the teaching of the church. His model was no more successful in predicting motions of heavens than Ptolemy's work. Okay, so what's parallax? The definition of parallax is that it's a displacement or difference in the apparent position of an object viewed along two different lines of sight, and is measured by the angle or semi-angle of inclination between those two lines. The term is derived from a Greek word, parallaxis, meaning alteration. Nearby objects have a larger parallax than more distant objects than when observed from different positions, so parallax can be used to determine distances. One of the simplest ways of observing parallax is when there is a clear sky at night and you're walking home or driving home over a long distance, the stars appear to follow us. However, we can explain that a little bit more clearly. Here's a diagram showing two different viewpoints of a celestial object with a distant background, or even an object on Earth with a distant background. From viewpoint A, the object appears to be against the blue background, and from viewpoint B, it appears to be against the red background. So is there a simpler way that we can demonstrate this? Okay, we can. You hold your forefinger, your index finger, close to your nose, about 10 centimeters or less away. Close first one eye and then the other. What happens to the apparent position of your finger? Gradually move your finger further away and repeat the process. What happens to the apparent position as the distance increases? Another demonstration that we can do is to now hold our finger against a more distant object. And what happens to the placement or appearance of the object as you look at it first of all with your left eye and your right eye closed, and then with your right eye and your left eye closed? Now here's an interesting gentleman, Tycho Brahe. He was a Danish nobleman, and at the age of 2, his uncle stole him from his parents. And his parents seemed to be okay with this, so perhaps he wasn't such a great toddler after all. He became a philosopher, he became an astronomer and a mathematician, and was a rather colourful character. He lost his nose in a maths-fueled duel. Well, obviously there was no internet for anyone to check who was right or not. He then had to wear a prosthetic nose. Most of the time he wore a copper one, but he did have a silver and a gold one for special occasions, and he was pretty wealthy. He did study the night sky and plotted movements of stars with great care and accuracy, so he wasn't dueling all the time. Now it has been suggested that he may have inspired Shakespeare to write Hamlet. Hamlet was a Danish nobleman, and he was murdered. And Tycho Brahe was murdered, and there are suggestions that he was murdered by mercury poisoning by his assistant Johann Kepler. Johann Kepler then became a famous astronomer himself. So Tycho Brahe was working obviously in the late 16th century, and his model combined geocentric and heliocentric ideas, that all planets except the Earth revolving around the Sun, and the Sun revolved around a stationary Earth. He looked for parallax shift but couldn't detect it. Slight shift in the position of stars due to Earth's movement around the Sun was what he was looking for, but he couldn't see it. After his death, Johann Kepler, his assistant, then took over. So he inherited all of Brahe's meticulously gathered data. See how he benefited after Brahe's death. He applied Brahe's data to Copernicus's idea and came up with a heliocentric model with planets moving around the Sun in ellipses, not circles. Kepler developed laws. First of all, the law of ellipses. Each planet moves in ellipse with Sun as the focus. The second law, the law of areas, the speed of planets along their elliptical orbits is such that they sweep out equal areas in equal periods of time. The closer a planet is to the Sun, the faster it must travel along its orbit in order to do this. So his third law, the law of periods, the time period t of the orbit of a planet is related to the average radius of the orbit as follows: t squared over the radius cubed equals k. T is the period in years, r is the radius in astronomical units. 1 astronomical unit is the average radius of the Earth's orbit. Therefore, when comparing two planets, t squared over r average cubed of planet A is equal to t squared over r cubed average of planet B. More on Kepler. The law of periods enabled him to make calculations of relative distances of planets in the solar system. He predicted the motion of the planets with greater accuracy than Ptolemy. Kepler's laws were based on observations. They could predict, but they couldn't explain why. Okay, our next astronomer is Galileo Galilei, probably one of the most famous astronomers, and you will certainly have heard of him, even if it's only through the Queen song. He was a physicist, first person to point a telescope at the night sky. He discovered Jupiter's 4 moons, orbiting Jupiter, not Earth, as previously believed. He was warned by the Church to stop advocating Copernican model, but he ignored the warnings. He wasn't as scared of the Church as Copernicus was. And unfortunately, that placed him under house arrest for the last 9 years of his life. Sir Isaac Newton, we have all heard of Newton's laws of motion, but he also contributed to astronomy. He explained planets' behaviour. He combined ideas about motion and used Kepler's laws of periods to determine that the force applied must obey the inverse square law. He used Kepler's law of areas to determine that the force applied must be a central force and it always acts along a line joining the Sun and the planets. And there's our favourite law, the inverse square law, that the gravitational force is proportional to 1 over the distance squared. Newton then developed his law of universal gravitation. The gravitation force of attraction acts between any 2 objects found in the universe. Mathematically, where F equals the magnitude of gravitational force, G is the universal gravitational constant, M equals the mass of the planet or bodies, and R is the radius. In brief, F equals G, mass 1 times mass 2 over R squared.